Now, in any cooling that takes place, what happens is that, for argument's sake, we are at 30 degrees Celsius, dry bulb, over there, and 25 degrees wet bulb. So we look at 25 degrees wet bulb over there. That point. Now, if I had to say that I want to cool down to 25 degrees or 20 degrees and 50% relative humidity. So I want to come from, here's 20 degrees. And there is 50% relative humidity. Now, I always, look, perhaps I'm an old fool, but anyway, I always color in this line, and I can tell you why. The number of times that I've worked out a whole thing, and I've assumed that I'm on the 50% relative humidity, whereas I find that no, I was on 40% relative humidity, or no, I was on 60% relative humidity, and everything is wrong thereafter. So I always just, on this chart, make sure that I've got that thing colored in. It just helps me. Might be a tip for you. So in other words, 20 degrees and 50% relative humidity is over there. Now, how do we get there? First of all, we are moving in that direction. So in other words, remember what I said about sensible heat? So if you move in that direction for sensible heat, we are cooling. If we're moving in that direction, we are heating. And we are wanting to move from that point there to this point over here, which means that we're moving in that direction. So it's going to be sensible cooling. Now, the other thing is that we're moving from a point of high moisture content to a point of lowered moisture content. So what has got to happen? First of all, we got to make things cool. And the only way that we can, and on top of it, we've got to get rid of water. So now how do we get rid of water in this particular case? And the only way we can shed water is by, first of all, moving towards the saturation line. So the first move that this thing will make would be towards the saturation line. So as we're cooling, the high quantity of moisture that you got over there would touch there, and it would start, in the minute it touches that point, the saturation line, it will start shedding water. So it sheds water all the way down to here. So there we go, we're shedding water. And then, when it gets to this point over here, it heats up again until it gets up to 20 degrees. So in other words, we've then effected a straight line process over there, in which we've had a straight line going there, shed water all the way down, and then a straight line process back to 20 degrees Celsius. In the same time, what we've done over here is that we've gone from 0,018 kilograms per kilogram of dry air down to 0,0072. So in other words, if you look at it, on my calculator, I'll be able to show the magic. We've got 0.018 minus 0.0072. We have had a change of 0.0108 kilograms per kilogram of dry air. So what you can pick up from this thing, if say for argument's sake we were pushing 100 kilograms per second, or 1,000 kilograms per second, so multiply that by 1,000. So we will be draining out 10.8 kilograms of moisture per second. So that is the importance of that particular scale over there. Right. The next thing that we'll be looking at is that if we're moving from that point to that point, we also then want to know how much energy do we have to put into a coil to effect cooling and dehumidification. Because remember now, in moving from that point to that point, we have done sensible cooling and we have done dehumidification, because we've moved in that direction, so we know that sensible heat has now got less, and we know that we've moved in that direction, and if that thing is anything to go by, we have dehumidified. So we've now affected what is known as now sensible heating, or rather sensible cooling and latent cooling. So we've had a combination of sensible and latent cooling over here. Now, to effect that, we have a look at this and we say, right, that point over there is about at 71, 72, 73 kilojoules per kilogram. And this point over here looks around about 36 kilojoules per kilogram of dry air. So if we had to say to ourselves, right, so 73 minus 36, 73 minus 36 gives us 37 kilojoules per kilogram of dry air. So if we're moving 1,000 kilograms of dry air, we're looking at 37,000 kilojoules to effect that. As you'll notice that the amount of airflow determines the amount of power that has got to be put into the coil, or the amount of energy that's got to be put into a coil. So it's quite a deciding factor when it comes down to the size of the plant. Right. Now let's have a look at a couple of small examples over here. Let me get some more psychrometric charts. I actually had all these things lined up to bring into class, but then the Rona arrived and that was the end of it, eh? It's almost surreal. Okay, so let's say I'm just going to deal now with sensible cooling or heating, okay? Right, so let's say that we are doing sensible cooling from 35 degrees and 35 degrees dry bulb and 20 degrees wet bulb. From that point, and we'll put a little block around it, and just remember these little blocks and circles that I draw on here are not just for making it look pretty, it's to make it stand out, because this chart can become a bit messy eventually, and if you don't follow some sort of rigor with regards to numbering and those type of things, you're going to find you're going to come unstuck. So let's say that's point number one. And we're going to just be sensible cooling to 20 degrees. So 20 degrees, and because we're not shedding any moisture, it is going to be a straight line move. There's 20 degrees, so we're coming along like that. 20 degrees. State point 2. Block around it and a 2. What can I ask you about this thing? I can ask you what is the starting temperature, and I can ask you what the ending temperature is, and you'll think that I'm like lost my marbles, because that's what I would be given in the exam, in the test. But what I will be saying is how much energy was affected to move that way. So let's say the mass flow is equal to 0,5 kilograms per cubic meter. Kilograms per second. That's what we're moving, 0,5 kilograms per second. Sorry, not cubic meters, kilograms per second. So now I need to know how much energy is expended in this particular move. So what I do is I just say, right, let's have a look here. Come down, and we find that that point is 51, 52, 53, 54. So 54, thereabouts, good enough, kilojoules per kilogram.